Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Before we proceed, I kind of like to request those members of us who have not subscribed to kindly subscribe, engage us in the comment section, and also ring that notification bell to be getting updates on our various discussion we do in mathematics and sciences. I also like to encourage us to be visiting our description boxes. I'm going to put a link there in terms of a playlist, which is going to consist of topics under a similar discussion. Now, that's going to be a range of our discussions which we have already done, and some of them which we are going to do. Of course, I'm going to put them as additional topics in that particular case. Now, in our discussion today, we're going to analyze the concept of the equation of motion of a simple harmonic oscillator. And in our last discussion, I had basically given this particular representation for that particular equation, which we had derived from considering the total energy of vibration of course, as this simple harmonic oscillator as the total of kinetic and potential energy. Now, we had given this one in terms of Hamiltonian, which is equivalent to the kinetic energy plus potential energy. And in this case, we had considered this one to be given in terms of the product of half mass and the square of velocity given as such. Whereas this one, we considered it to be elastic potential, which we had given in terms of half kx and the square of that. So this specific equation culminated in an equation of what we referred to as the simple harmonic oscillator, whereby we had given this one in terms of the equation of motion of that simple harmonic oscillator. And this was represented in terms of kx, whereby we said the kx is k is a spring constant, x is the displacement, and then this one was the summation of m, where m is mass and the second derivative with respect to time given as the t squared. And this, of course, was equivalent to 0. So in this case, we had given this one as the equation of motion of a simple harmonic oscillator. And basically, I had mentioned that this is going to represent the second order differential equation, which solutions can be given in terms of the cosine and the sine function given in terms of this particular representation. So I can just give this one in terms of a, the cosine of omega naught t plus phi. So I'm going to basically just give these particular representations. But basically given an implication or analyzed or given in a detailed form what this basically aspect of the amplitude, this of course angular frequency, the time, and the aspect of phi, which is a fixed phase, is. So in this case, I'm not going to go into details, but we said that the solutions for this specific second order differential equation are going to be given in terms of the sine and the cosine. And of course, we had given the one representing the cosine given in that specific order as such. So in our discussion today, we're going to look at deeper details of this specific equation and find a way in which we can represent, of course, other forms of this particular representation, of course, in terms of the Hamiltonian. And of course, that's going to assist us in trying to find a way of trying to represent this specific aspect of particularly the aspect of mechanical energy, which I've given in terms of this specific representation. So therefore, we are going to consider these two specific aspects, but I'm generally going to use this solution for the cosine, which is going to give us a way of representing this mechanical energy in terms of h, and that's going to form basically main objective in this particular discussion. So we had basically mentioned that from this specific equation, we can have this aspect of the amplitude, perhaps the amplitude in fixed phase, and the two concepts of the trigonometric functions represented. And as I've said, for us to find this specific mechanical energy, so I'm going to give this one in terms of the mechanical energy, perhaps in terms of, let's give this one in terms of h. So we're going to represent our h in terms of t, which is kinetic energy, and of course the potential. And we're going to consider this specific elastic and elastic potential and the kinetic energy as I've said. So in this case, our element for x is going to be represented using this specific equation, which I've given as one of the solutions of this second, of course, order differential equation. And of course, that's going to form a, the cosine of omega naught t plus phi. So in considering this one, then therefore we're going to have this one as our x. So for us to find the aspect of velocity from this specific equation, we're going to have our first order differential equation, which is going to be given in terms of d over dt, of course, which is going to be giving us a negative a omega naught the sine. So this, from our differentiation of trigonometric functions, we're going to see that the differential, the derivative for the cosine is going to be negative sine, and therefore that's going to give us omega naught t plus. So I'm going to do away with this. Perhaps we expand this space up to this point. So we're going to have this one as omega t plus phi given as such, and that's going to form our first derivative. Now the first derivative of x, which I've said, is of course going to give us an element of velocity, and then we're going to find our second order derivative with respect to time given us. So we're going to find another derivative of this specific aspect. So the derivative of a sine function is going to be giving us a cosine, and of course we're going to see that we're going also to have this specific element of so this is going to be angular frequency given as a square. So for the second order, we're going to have the cosine of omega naught t plus phi. So we're going to follow this procedure in a slower pace so that we are going to all of us understand. Therefore, from the above equation, we can see that for us to represent this specific equation, which we had given in terms of kx plus m, the second derivative of x with respect to time is equivalent to 0. So this specific equation for equation of motion of a simple harmonic oscillator can be represented using this specific aspect. So we have the element of x which can be substituted in this, and then we have a second order derivative, or a second derivative of x with respect to time, which has been given in this particular case. So therefore we can have a substitution for this and see how we can represent this specific equation. So perhaps I'm going to reduce my size of the writing so that this is going to be enough for us. So we're going to have this one by doing a substitution, whereby we're going to have our k and then we're going to have our x. So our x in this case is going to be represented using this specific representation for a, the cosine over omega naught t plus phi. So I'm going to have it given as a cosine over omega naught t plus phi. And then this one, I'm going to have it given. So this is going to represent our kx. So plus m and the second derivative of this specific element of x with respect to time. So this is going to give me the second aspect of the equation of the second derivative, which basically is going to represent the element of a negative. So I'm going to have this one as negative a, and then I'm going to have m. So this m is basically the m which I'm going to obtain from this equation of motion, of this simple harmonic motion. So it's going to be negative a m and then omega squared, omega naught squared, the cosine of so I'm going to have a continuation, omega naught t plus phi given as such, and that is going to form my substitution for the first case, and this is going to be equivalent to 0 as I had said. So given as that one. So this is going to be representing my substitution. So if we try to look at this specific point, we can consider the rearrangement of this equation in order for us to find what basically this specific equation is going to represent. So having said that this specific aspect of the first part and the second one is going to be equivalent to 0, and this is going to give us a negative value. So if we take the second part of the summation of this over the equal sign, is going to be forming our positive part. So we shall have this one represented in terms of the values of k into a, the cosine over omega naught t plus phi, and then we shall have this one is equivalent to a m omega naught, so that's going to be a square of that, the cosine of omega naught t plus phi. So this is going to be the equation equivalent to this one, having taken the second aspect of the sum over the equal sign. So if we try to consider this one, we're going to have this particular element over a, the cosine. So if we have a the cosine of omega naught t, and a, the cosine of omega naught t. So the remaining elements of m omega naught, the square of omega naught is equivalent to k. So therefore we can have this implication whereby k is equivalent to omega, the equivalent to m omega naught squared, given as such. And remember this one kindly, so we're going to pick it from this specific point. So if we have obtained the value of k from this specific point, then therefore we're going to consider the concept of elastic potential. This is going to be forming in our second part, which we had mentioned basically. We can consider either the first or the second part, but if you look at the concept of elastic potential, which we are going to consider in terms of V, so this is going to be giving us the value of a half kx squared from our previous discussion. And therefore, if we try to consider this specific aspect of k and the square of x from this specific point, we're going to come up with a version of the equation which we can give in form of this specific representation, whereby v is equivalent to so we're going to have a half k, and then we're going to have the square of this one. So we can have this specific aspect of a cosine over omega naught t plus phi, and then we're going to have the square of this one. So this is going to represent the elastic potential of this particular system, and from there, of course, we can just find an evaluation for this, given as a half k. So we're going to have a square of this one, a squared. This is going to be the amplitude, having been a portion of this specific squared function, then therefore it's going to be a square of that one, and then the square, the cosine square of omega naught t plus phi, given as such. So that's going to be forming a portion of the equation which we have given using that specific order. So this is going to be forming our elastic potential, which we have given in this specific, of course, function. So if you consider the second case for the kinetic energy, which is going to, so we have found an evaluation for this one. We're going to consider the kinetic energy, which basically is given in terms of t. As we said, this is going to be half mv squared. So I mentioned from this specific case that our second the first differential equation is going to be forming what we refer to as our velocity, and this was a derivative of what we referred to as, of course, the x function, which I have just given us that. Now in this case, having said that it's going to form the sum of our mechanical energy is going to form the sum of the two. Therefore, as well, we can find a representation for kinetic energy using this specific function, whereby we're going to see that, let's have this one given as such. So from this point, perhaps I can use this one. I hope that we have understood the previous discussion we had on what we have just done away with. So therefore, we're going to have a kinetic energy given in terms of half m, and we had said that we're going to have velocity as the derivative of x, which is of course the value for x, which we have said it was equivalent to this one, with respect to time. And for our kinetic energy, this is going to be a square. So the first derivative, which is going to give us velocity, is going to be giving us our square of this one. But we have said that the first derivative is going to give us the function of this one. So therefore, we are going to have this one given in terms of dx over dt. The square of this one is equivalent to the square of this, which is negative a omega naught, the sine of omega naught t plus phi, and that is going to form our function for the square of this first derivative given as such. So this basically is going to reduce into a function which is going to be given as such, whereby we're going to see that if we have this square of this negative function, it's going to be a positive, and therefore we're going to have the square of the square of omega naught, and then we are going to have the square of the sine of omega naught t plus phi given as such. And if we try to consider, this is going to be therefore representing our second derivative. So if we consider the concept of t, which of course included half the element, so these are going to be the coefficients of half m. So therefore we can have this one written in terms of a half m a squared omega naught squared the sine square of omega naught t plus phi. And this therefore is going to represent the element of what we refer to as kinetic energy. So therefore we can find the total, of course, a function which is going to represent both the kinetic energy and of course the elastic potential given in terms of mechanical energy, which is the summation of the two aspects of T and V, which I've mentioned in this particular case. So I'm going to have a sum of the two, and I'll try to see what they are basically going to represent. So if I have this one, then therefore the mechanical energy is equivalent to the values of a half ma squared, which is so I'm going to do a substitution for this particular function of t, and then we're going to have omega naught squared the sine of omega naught t plus phi, and then I'm going to have this one added to the elastic potential in this case, which is a half k a squared the cosine squared over omega o t plus phi. So if we try to consider this one, we're going to have a specific aspect whereby the concept of or the coefficient of half k a squared is going to be this and this one, and of course we're going to have this particular function whereby we're going to, so in this case I would like us to take note. We had found the value of k equivalent to the product of m and omega naught. So in our first equation we're going to have the element of m and omega naught, and therefore these are going to form the concept of k. So in this case the remaining elements are going to be given in terms of k a squared, and then we're going to remain with this trigonometric function. So therefore we're going to have this one multiplied the sine squared omega or omega naught phi, and then this one plus, so basically I'm going to do away with this so that we have that one given as such, and this one is going to be of course a plus. Basically I can just do away with this so that we have the larger square brackets catering for all of them. So we're going to have this one as the cosine squared omega naught, and then we're going to have that one, and then we close the brackets. So if we try to consider this specific function, basically it's going to be the sine squared of a function plus the cosine squared of a function, and from representation of our trigonometric function, this is going to form a unity from the first of course identity. So therefore we're going to remain only with this specific section of the function, which is going to be represented as perhaps I can just give it in terms of just here. So we're going to remain with this specific function, which is going to represent mechanical energy given in terms of a half k a squared given as such. So this is how we can represent the mechanical energy of course this oscillator, or what we refer to as a one-dimensional simple harmonic oscillator. And of course I presume that we have understood, although this specific process was lengthy, the simple procedures which I've done are going to assist us in order to come up with this specific equation. So in case we mention it in any of our subsequent discussion, then therefore this specific video is going to be coming handy in assisting us understand the same. So that is it for now, guys. Kindly check our description boxes for various links of other similar videos. Engage us in the comment section and subscribe for more so that we can be having a healthy discussion of various topics in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.